Good afternoon. My name is Gerardo Martí. I'm sorry I got the flu a couple of days ago, so perhaps my voice will not be very well, and as the colors are not very good here. Tenkate is a very old company. Tenkate was founded 311 years ago in the Netherlands to manufacture sailings for the boats going to the Indias to trade with different materials. In the 50s, Tenkate realized that sails were not a good business, but they had a lot of experience in manufacturing textiles, so they switched to geotextiles. And today, Tenkate is the largest manufacturer of geotextiles in the world. Tenkate is also the inventor of the geotextile container. In the early 60s, there were some big storms in the Northern Sea that flooded the lowlands in the Netherlands, and they had to rebuild the berms that protect those lands. And instead of putting small bags of sand, Tenkate proposed to use big bags of sand, 100 cubical meters. And they invented what they call the geotube. Today, I'm going to show you one example of the use of this technology to dewater contaminated materials that needed to be dredged from the sea and use those materials to create a platform for containers in the port of Santos in Brazil. Mr. Tom Stevens is vice president in Tenkate. He has been my mentor. I do not work for Tenkate. I'm the agent for Tenkate in the southern cone of Latin America. I'm also, my company is distributor and turnkey solution provider for projects like this. So I have a lot of experience, and that's why Tom asked me to come and give this presentation on his behalf. This is the Embra port terminal located in the port of Santos. I'm going to go fast because the concept is very simple. So if you have questions, you can make them later. This is the project, okay, to create this piece of land to have containers. And here is the pier for the boats. The project, 85 hectares total area, 2,000 million TEU. It's equivalent 20 feet container per year. 2 million cubical meters, cubical yards of bulk liquid per year. The pier length is 1.1 kilometer. Will be the largest terminal in South America, and has been rated as the most innovative port project in 2013. This is before. All this area signal here is what is going to be the terminal, and you can see that approximately 50% of this area, well, it is here, 50% of the project footprint was located in wetlands and tidal zone. 600,000 cubical meters from this area had to be dredged to allow the big boats to go into that area, and had to be disposed away. And to build this in a traditional way, they should have to bring fresh material from inland to build this solution. So the proposition by Tenkate was, why don't we just encapsulate this contaminated material, dewater it into a dewatering cell, and we save bringing fresh material from inland, and we do not use this contaminated material in a landfill. Okay, so 600,000 cubical meters of contaminated material had to be removed. There was limited available area for upland disposal facility. There was no place to take all this material. It required a large volume of imported fill and this was a traditional solution. Create this area that was smaller than they needed and bring materials from inland. So finally, the solution was to use geotextile tube dewatering technology to contain and dewater 600,000 cubical meters of contained sediments, create geotextile tube dewatering cells that are made with geomembranes to prevent infiltration of the contaminated water, and the contained, dewater, and consolidated contaminated sediments within the geotextile tubes would replace approximately 450,000 cubic meters of imported fill material. So it was a win-win if it was cost efficient, and it was. So this beneficial use of the contaminated sediments would significantly reduce project construction costs by $50 million. The parties, Odebrecht was the general contractor, Alonda is the distributor of Tencate in Brazil, was in charge of environmental engineering and environmental testing, and Jean Denil was doing the dredging. So this was the team. The design take the tidal flat area of the project up to 3.5 meters. The pictures will be much easier to understand. Construct geotextile tubes, the water cell. The water cell was 235,000 square meters in the tidal area, and install geotubes or geotextile containers 36.5 meters circumference, approximately 17 meters wide each, with a capacity to contain 35 cubical meters per linear meter at approximately 2.2 meters high. I will show you the design. And then cover these geotextile containers with 1 meter of a pavement system that I will show you. That is a quite interesting solution. This is the design of the geotube. It's 2.2 meters high, 36.5 meters circumference, and these are the different tensions that are produced, and then we never exceed 3 times the safety factor, and in this case, the safety factor has been around 4.5. So we are far from any rupture in the geotextile. We could take it even higher to 2.6 meter high without any problem, but 2.2 meters was designed. And this is how we calculate the total volume, and the total volume was to be 415,000 cubical meters of estimated dewater volume. Estimating that the consolidation would be 55%, but in fact we reached 57% content solids inside the geotubes. This was the objective, 55%. The final consolidation was 57%. So what did we do? First, we did a test without geotubes. This was just a test to check how the consolidation with different levels of material to get pressure on top of the tidal area, and then drain wicks were placed in different areas in different densities. Some areas with high density of drain wicks, other areas with less density, more pressure, less pressure, to check how the consolidation of the soil would be, and once that determined, they began the construction. First thing is check the chemicals. We need to use polymers because the dredging material has a lot of fines. It has a lot of sand, but a lot of fines and a lot of contaminants. Then we have to consolidate all this, and for that we use flocculants or polymers. I will show you later all that process, and this is how we do the test, a small test in a very small geotextile container. We did many different tests under different conditions. This is the quality of the water flowing from the geotextile container. We need to get very clean water because the water is going to be returned to the sea. Different tests, and then we checked in different conditions the percent solids inside after 1 week, 2 weeks, 3 weeks, etc. And so we got the best composition of polymers. We already saw this. And then this is the berm. Here would be the pier, and the pier has to be on these columns. And this was the berm. On top of the berm, there would be 1 meter of material, different layers of gravel, and on top 10 centimeters of pavers. Why pavers? Why not concrete? And this is to use 10, 11 layers of containers, so a lot of weight. And this is because it could happen that over time there could be some settlement. If you have concrete, you will have to break the concrete, repair the settlement, and concrete again. But if you have pavers, they develop a machine that takes the pavers out, repairs, and put the pavers on, and it is perfect. It has not been necessary to do that, but it was prevented that could happen. Okay, so the final design is for 187 ton force per square meter. It's 887 tons per square meter. This is the resistance of this. This is the consolidated dredged material. Then there is 1 layer of 20 centimeters of compacted remnant fill, then gravel, 35 centimeters, another layer of 35 centimeters of gravel, and then the pavers on top for the height of 3.5 meters above sea level. And finally, the bearing, where is it? Here it is. The bearing factor is 448 tons per square meter. And the design is for 187. So I'm not an expert in this. I'm sure that any of you can teach me about this, but if you need, I can provide you more technical data, which leads to a safety factor, 187 448 divided by 187, to a safety factor of 2.42, which is fairly good. This is how we began. Build the berm, then took the water out, and built the watering cell. This is a second part of the project. Then we begin to put the geocontainers here, very long. This is a facility to prepare the polymer. We are talking of dredges that were pumping 1,000 cubical meters per hour of contaminated material at approximately 4 minutes, I'm okay. At approximately 8% solids content. So the amount of polymer were cubical meters per minute of prepared polymer. So we had all this. This was for measuring solid content so that the injection of polymer could be adjusted depending on how much solid came from the dredgers. And this was the system to control the level of the different polymer tanks. These were the injectors of polymer. This was the main pipe that taking the dredged material to the geotubes. And this is where the polymer was injected. And here is the mix produced. And then all these pipes taken to the different geotubes, et cetera, et cetera. Now, the second part, the same. Here you can see that it begins to be covered, the geotubes begin to be covered with different layers. First, they were compacted with 4 or 5 meters of overburden material to compress and finish the watering. Then they took the overburden material away and finished it. And here it is in operation. So still, it has to grow in this, and it has to grow in this direction to finish being 1.1 kilometers, but it is already in operation. This is the real thing in 2014. This is the project as will be in a few years when they finish it. What else I can tell you? That now we, conclusions about this. Geotechnical environmental standards of practice and modeling tools are available to predict the actual field results of geotextile tube technology. Geotextile tubes can be used to contain the water and consolidate certain marine contaminated sediments to a sufficient degree of consolidation and in significant quantities such to allow for use as a structural fill. We have done this many times in different projects, so it's no surprise for us. And with this, we could save the Hembra port $50 million using this technology. What are we working now? What is coming next? Puerto Pesquero Capurro in Montevideo, here in the other side of the river. This is area, this is ANCAP. The refinery, all this is filled with contaminated mud. What they do typically, they take the mud and they send it to the center of the river. And the Port of Montevideo said we must try to do something positive with this contaminated mud and not send it to the river. So what they are going to do, they are going to a land reclamation, approximately 15, 16 hectares here. We are going to take this, are going to do exactly the same as in Hembra Port. 1 million cubical meters of contaminated mud, and at least 650,000 of that is going to be put here to create this park with a port, etc., etc. So this works, and it is cost effective. Of course, it is always cheaper to take the contaminated mud and send it to the river or to the sea. But if you are conscious environmentally, you can do things better. Thank you.